In this video, we'll decide if these two pairs of molecules are enantiomers, diastereomers, or identical. Now, I chose a cyclic compound as our example problem because I want to make some notes. If you see a cyclic compound and there are two of the same groups opposite of each other, whether it's on a wedge or a combination of a wedge or a dash, if they're opposite, they are achiral, they are diastereomers. Okay, but I want to remind you, don't fall for the trick of thinking about cis or trans in these contexts. Think about R and S priority groups. Okay, let's solve this problem. Now, the biggest peeve I have with these types of drawings is it's intended to throw you off. So I like to draw it again, but this time flatten it. And I'm just going to assign that everything that is down is going to be on a wedge because it just saves a lot of issues later on. If you put it on a dash, you're going to have to think backwards when you start assigning priorities. And I like to just not write out the hydrogen here because it's already implied. Since if I write out hydrogen, it makes the picture more cluttered, and it just makes the priority stuff a bit more complex and unnecessary, just unnecessary work. Okay, now you see it's very nice that we didn't add the hydrogens in here because it's just simple, it's very straightforward. You can tell immediately what are going to be your priorities. So here, we'll call this carbon 1, okay? Carbon 1 has a chlorine. This is going to be important. Carbon 1 has a chlorine. This is a priority, the second priority is here, the third priority is here, so hydrogen is just fourth and it's on a wedge, perfect. It's on a dash, so perfect. So on carbon 1, this is an S rotation counterclockwise. For the top, our priority group is actually going to start down here, and then it's here, and third is methyl. So the fourth is on a dash on hydrogen, perfect. This is carbon 2 with an R rotation. Here, this is something I want to stress. Where is carbon 1? Is it still here? Because the first picture, carbon 1 was down here. But is it still here? No. So this is one of the reasons why I chose this example, because it's just such a mean trick to play on you. Carbon 1 is now up here. So let's just find the priorities here. This is 1, this is 2, this is 3. Hydrogen is on a dash. This is carbon 1 with an R rotation. Down here, this is 1, 2, 3, counterclockwise S rotation. Okay, so now you can compare. Carbon 1 was S, but now it became R. Carbon 2 was R, but now it became S. Therefore, these two are actually enantiomers. Now, the trick that they try to play on you here is if you thought that let's just say you didn't write carbon 1, carbon 2, and then you just kind of horizontally compared, and it seems like, well, it looks like here it was S, and now here it's still S, and then up here it was R, and up here it's still R, so maybe these are identical. If you make that conclusion, that is bad. Don't do that. So this is why it's really important to consider which carbon of reference your branch is on, okay? So this is carbon 1 as we called it, so the carbon 1 is up here because it still has a chlorine. Carbon 1 is the thing that has a chlorine. Be really careful about that. And in terms of other questions that ask you what is an enantiomer, which pair is an enantiomer or which pair is a diastereomer, the process is the same. Find the R and S configuration and put it on a carbon of reference, compare it. If all chiral centers have changed their configurations from S to R, if all of them did, then it's an enantiomer. Okay, let's write that down. Enantiomers are when, let's say you had an SR and now it became an RS, or if you had an SS and then it became an RR. Diastereomers is where only one chiral center inverts its configuration, like you started with SR but it's still S, but the other one inverted into R. Or this is SS, but only one of it changed to R. So that's a diastereomer. So any questions you have, just check the RS configuration around its chiral centers to determine if it's an enantiomer or diastereomer. And if the two things you're comparing are identical, they have the same configurations on their chiral centers, then they are identical, okay? Another really important thing I'd like to note is Fisher projections, finding if two Fisher projections are enantiomers or diastereomers. Remember, everything that is on a horizontal line in a Fisher projection is actually on a dash bond, is actually on a wedge bond. So if your hydrogen is on a wedge, you want to remember that if your rotation looks like S, it's going to be R. And one other thing is, let's say you have a long complex molecule and it ends with something like this. Or if you just have something that looks like this, and then you have some molecules on each of these ends. The way that you would identify if they are R or S configurations is you hold one solid line by the stem and then you rotate the three groups. So that means if your hydrogen was not on a dash, let's say if it was on a solid line, you would rotate the three groups to put the hydrogen on the dash. Now I have another short clip on this particular point, so I'll leave it at that.